Hello everyone. Today I would like to walk you through a very important topic in Kubernetes. How to run database safely using persistent storage. In most Kubernetes tutorials, we often see stateless applications like web servers or API. They are simple, easy to scale, and easy to replay. But in real-world system, things are different. Every system depends on data, and especially database. And database introduce a critical requirement. Data must never be lost. So the big question is, how can Kubernetes, a system built around ephemeral containers, handle something permanent like a database? In this presentation, I will answer that question step by step. First, we understand the problem. Then, we explore Kubernetes storage solution. Next, we design a real architecture. And finally, we validate everything with a live demo. Let's begin. The core problem. Containers are ephemeral. To understand the solution, we must understand the problem. In Kubernetes, everything revolves around pods and containers. But containers have a key characteristic. They are ephemeral, meaning temporary. Let's imagine a simple scenario. We run MySQL inside a container. We insert some data, then the pod restarts. What happened? All data is gone. Why? Because by default, data is stored inside the container file system. And when the container is destroyed, the data disappears with it. This behavior is perfectly fine for stateless application. But for database, this is unacceptable because data is critical. Data loss is a system failure. So clearly, we need a better approach. The solution, decoupling storage from containers. Kubernetes solves this problem with a very powerful idea. Decouple storage from the container life cycle. Instead of storing data inside containers, Kubernetes introduces a separate storage layer. The architecture looks like this. Let's break it down. Persistent volume (PV) represents real storage. Persistent volume claim (PVC) is how application request storage. Storage class helps dynamically create storage. Now something very important happens. Even if a pod is deleted, the containers disappear, but the data remains safe in the persistent volume. This design gives us data persistence, flexibility, independence between computer and storage, and this is the foundation for running database in Kubernetes. From stateless to stateful thinking. At this point, we need to change our mindset. In Kubernetes, application falls into two categories: stateless application, web servers, and API. These can be replaced anytime without impact. Stateful application, database, and MySQL. These require persistent data, stable identity. And here is the key insight. Kubernetes treats these two types differently. From stateless app, we use deployment. But for stateful app, we use something more advanced. StatefulSet, the right tool for database. To manage stateful application, Kubernetes provides StatefulSet. StatefulSet is designed specifically for system-like database. It guarantees three important things. First, stable pub identity. Next, stable network identity. And next, stable storage per pub. This is very important. This is very different from deployment. In deployment, pubs are interchangeable. In StatefulSet, each pub is a unit and persistent. This is exactly what database need. In our project, we use StatefulSet to run MySQL. So even if a pub restarts, it keeps the same identity. It reconnects to the same storage, and the system remains consistent. System architecture, putting everything together. Now let's look at the pull system. The architecture is simple, but powerful. Here is how it works. The user sends a request. The web application processes it. The app stores or retries data from MySQL. MySQL writes data into persistence volume. From the infrastructure perspective, web app run in a development. MySQL run in a StatefulSet. Storage is managed by PV or PVC. This separation is very important. It allows us to scale the web layer independently, keep the database stable and safe. This is a common production pattern. Application flow from request to storage. Let's make this more concrete with our demo application. The application provides two simple APIs. When a user sends a pub request, the app receives the message, then store it in MySQL. When a user sends a GET request, the app queries MySQL and returns on message. Behind the scenes, every piece of data goes into persistent storage. So even if the app restarts or the database restarts, the data remains in it. Kubernetes component. Who does what? This system is powered by several Kubernetes resources. Deployment, manage web app pub. StatefulSet, manage database pub. Service, enable communication. PVC, request storage. PV, provide storage. Each component has a clear responsibility. And this modular design gives us scalability, maintainability, reliability. This is one of the reasons Kubernetes is so powerful. The key test: does data survive? Now comes the more important part. We test where the data really persists. Step: first, insert data into MySQL. Next, delete the database pub. Next, query the data again. What happened? The data is still there. Why? Because data is stored in persistent volume, not inside the container. Kubernetes recreates the pub automatically and re-add the same storage. This demonstrates a self-healing and reliable system. Production thinking, backup strategy. But in real-world system, persistence alone is not enough. We also need backup strategy because hardware can fail, data can be corrupted. Common solutions include MySQL Dump or cron job for schedule backup or volume snapshot. In typical flow, database, then backup jobs, then cloud storage. This ensures data recovery, disaster protection. So always remember, persistence protect against restart, backup protect against disaster. Now let's review the follow-up projects